Step outside on a clear night and look up. Somewhere past the porch light sits a number, the size of the entire universe. One your mind was never built to hold. For the next 20 minutes, I want to walk you toward that number, one step at a time, from your street to the edge of what light has ever reached us, until the scale finally breaks something open, in how you see your own place in it. Start with something you already know. Your house, your street, the town you grew up in. All of it fits inside one photograph. Taken from low orbit 400 kilometers up, roughly where the International Space Station circles Earth every 93 minutes. Pull back further and your whole country shrinks to a patch of color on a blue and green marble. Pull back once more and Earth becomes a pale dot, 12,642 kilometers wide, floating alone against black. Your city has vanished. Your street was never visible to begin with. This is just the beginning of the pullback, and already the ground beneath your feet feels smaller than it did 5 minutes ago. Now shrink the sun down to the size of a basketball, about 24 centimeters across. At that scale, Earth sits roughly 24 meters away, smaller than a grain of sand. Mars sits 37 meters out. Jupiter, the largest planet, sits 124 meters away, still smaller than a golf ball. Neptune, the last official planet, sits nearly a kilometer from that basketball. Between Neptune's orbit and the basketball, space holds almost nothing, just a scattering of rock and ice, and one blue speck you happen to live on. Even the asteroid belt, which sounds crowded in movies, amounts to mostly empty court. Spacecraft have crossed it without a single collision. The Voyager probes, the Pioneer probes, New Horizons, all of them slipped through without incident, because rock in that belt is spread across hundreds of millions of kilometers. In 1977, NASA launched Voyager 1 to study Jupiter and Saturn. It has been flying at roughly 61,000 kilometers per hour for 48 years, and it left the planets behind decades ago. In 2012, it crossed the heliopause, the boundary where the sun's solar wind gives way to interstellar space, becoming the first human object to leave the solar system's bubble. It is now over 24 billion kilometers from Earth. A radio signal from Voyager traveling at the speed of light takes more than 22 hours to reach mission control. Even at that distance, moving at that speed since 1977, Voyager would need about 40,000 years just to reach the neighborhood of another star. And it isn't even aimed at one. The nearest star to our sun, Proxima Centauri, sits 424 light-years away. A light year, despite the name, is a unit of distance. The length light travels in 1 year, moving at 2,999,792 kilometers per second, fast enough to circle Earth 7 times in a single second. Written out, 1 light year equals about 9.46 trillion kilometers. Multiply that by 4.24, and you get the gap between us and our closest stellar neighbor, roughly 40 trillion kilometers. Drive there by car at highway speed, and the trip takes about 45 million years. Longer than the 66 million years since the dinosaurs went extinct, but in the same order of magnitude. Fly there on the fastest spacecraft humans have ever built. The Parker Solar Probe at 690,000 kilometers per hour, and the journey still takes over 6,600 years. That is the distance to one star. Our galaxy holds hundreds of billions more. Our galaxy, the Milky Way, holds somewhere between 100 and 400 billion stars. Astronomers still argue over the exact count, because dust in the galactic disk blocks direct view of much of it. The galaxy spans about 100,000 light-years across, and roughly 1,000 light-years thick at the disk. Our sun sits in a minor spiral arm, called the Orion Arm, about 27,000 light-years from the galactic center, where a supermassive black hole named Sagittarius A holds roughly 4.3 million solar masses. The sun takes about 225 million years to complete one orbit around that center, a period astronomers call a galactic year. Since the solar system formed 4.6 billion years ago, it has completed only about 20 of those orbits. The last time our sun was in this exact position, the first dinosaurs hadn't appeared yet. The Milky Way itself ranks as an ordinary spiral galaxy, mid-sized among the billions of galaxies astronomers have cataloged. Not the largest, not the smallest, sitting comfortably in the middle of the distribution. Andromeda, our nearest large galactic neighbor, holds roughly 1 trillion stars. and sits about 2.5 million light-years away, the most distant object visible to the naked human eye. It is heading toward us at 110 kilometers per second. Astronomers expect the two galaxies to collide in about 4.5 billion years, merging over hundreds of millions of years into a single elliptical galaxy. Some researchers have already nicknamed Milky Way. Individual stars will almost certainly not collide. Space between them is too vast, but the night sky of any surviving observer would transform completely, filling with a second spiral wheeling slowly overhead. The Milky Way, Andromeda, the Triangulum Galaxy, and around 80 smaller dwarf galaxies together form what astronomers call the local group, a cluster spanning roughly 10 million light-years. The local group itself amounts to only a suburb. It sits on the outer edge of the Virgo cluster, a collection of more than 2,300 galaxies, centered about 54 million light-years from Earth. In 2014, a team of astronomers led by Brent Tully at the University of Hawaii mapped something larger still, using the motion of galaxies rather than their light, to trace gravity's fingerprint across space. They named the structure Laniakea, Hawaiian for immeasurable heaven, a supercluster containing roughly 100,000 galaxies and stretching about 520 million light-years from end to end. Every galaxy inside it, including our own, drifts slowly toward a gravitational center, called the Great Attractor. Tully's team found that the Milky Way sits near the edge of Laniakea, close enough to its boundary that we could plausibly belong to the neighboring supercluster instead, depending on where exactly the dividing watershed of galactic flow gets drawn. Even a structure 520 million light-years wide turns out to have a fuzzy border because gravity doesn't draw clean lines. Superclusters like Laniakea link together through filaments of galaxies and dark matter, forming structures cosmologists call the cosmic web. Follow one filament far enough, and it feeds into a node where several other filaments meet, a junction dense with galaxy clusters. Between the filaments sit voids, regions hundreds of millions of light-years wide, holding almost nothing at all, just a handful of stray galaxies, scattered across emptiness that dwarfs anything on this list so far. The largest confirmed void, called the Boyutis void, spans about 330 million light-years and holds only a few dozen known galaxies, a gap so empty that early astronomers who found it in 1981 briefly wondered whether their data had an error. Keep pulling back and you reach the observable universe. Everything light has had time to reach us, from since the Big Bang. It spans about 93 billion light-years across. The universe itself, according to measurements from the Planck satellite, turns 13.8 billion years old. Do the math and something breaks. Light hasn't had time to cross 93 billion light-years. In only 13.8 billion years, not even close. The resolution comes from an effect most people never learn in school. Space itself has been stretching the entire time that light traveled through it. A photon that left a distant galaxy 13 billion years ago set out across a much smaller gap than 93 billion light-years. But space kept expanding underneath it as it flew, carrying the galaxy that emitted it further and further away, so that by the time the light finally reaches your eye tonight, its source sits at a present-day distance of roughly 93 billion light-years, even though the light itself only traveled for 13.8 billion years. You are looking at where that galaxy used to be, stretched across a gap that grew while the light was in transit. Inside that observable sphere, astronomers using the Hubble Space Telescope in 2016 estimated roughly 2 trillion galaxies. A 2021 reanalysis with sharper data and better modeling cut that number down to somewhere between 200 billion and a few hundred billion. A reminder that even our best count keeps shifting as instruments improve. The James Webb Space Telescope, launched in December 2021, pushed the record for the most distant confirmed galaxy, back to JDS GSZ 14-0, whose light left its source about 290 million years after the Big Bang, when the universe had barely finished cooling. Enough for the first stars to ignite. Webb found galaxies at that age, already larger and more structured than early models predicted, forcing astronomers to revise how quickly the first galactic structures actually formed. Every new telescope has moved the frontier further back. There is no reason to think Webb's successors won't do it again. The observable universe marks only the limit of what light could reach us. In 13.8 billion years, nothing more. Beyond that boundary, called the cosmic horizon, space almost certainly keeps going, filled with galaxies whose light simply hasn't had time to arrive yet. And the boundary works in both directions. Because the universe's expansion keeps accelerating, some regions of space right now are receding from us faster than light, can cross the growing gap between us. Information from those regions can never reach Earth. Not in a billion years, not ever, no matter how sensitive our instruments become. Physicists call this a causal horizon, and it means entire regions of the cosmos, possibly holding their own galaxies, their own stars, their own unknown physics, are permanently sealed off from anything we could detect. We are not looking at the edge of the universe. We are looking at the edge of what we are physically capable of knowing, a very different thing, and one that keeps shrinking as expansion continues to accelerate. In 1980, physicist Alan Guth proposed a theory called cosmic inflation to solve several problems with the original Big Bang model, including why the universe looks so uniform in every direction. Guth's math showed that in the first fraction of a second, after the Big Bang, faster than 10 to the negative 32 seconds, space itself expanded by a factor of at least 10 to the 26, blowing a region smaller than an atom, up to a stretch of space several centimeters across. Almost instantly, if inflation happened the way Guth's equations describe, it likely didn't stop everywhere at once. Some versions of the theory, developed further by physicists including Andre Linde, suggest inflation continues forever in most of space, stopping only in isolated pockets, one of which became our observable universe. Under that model, called eternal inflation, the total universe extends far past our horizon, plausibly without any edge at all. Nobody has measured this directly. It follows from equations that correctly predicted other things we have measured, which counts as the closest science currently gets, to testing an idea about regions we can never see. Matter you could touch, every star, every planet, every person who has ever lived, adds up to only about 5% of everything that exists in the universe. Dark matter accounts for roughly 27%. Nobody has directly detected a particle of it. Astronomers infer its presence entirely through gravity, from the way galaxies spin faster than the visible matter in them should allow, and from the way light bends around galaxy clusters, far more than their visible mass can explain. Vera Rubin's measurements of galaxy rotation in the 1970s provided some of the earliest strong evidence for it. The remaining 68% comes from dark energy, a phenomenon discovered in 1998, when two independent teams of astronomers studying distant supernovae found that the universe's expansion, instead of slowing down under gravity as everyone expected, was speeding up. That discovery earned Saul Perlmutter, Brian Schmidt, and Adam Rees the 2011 Nobel Prize in Physics. Nobody knows what dark energy actually is, at a fundamental level. Physicists gave it a name mainly to have something to write down in their equations. That accelerating expansion drives a phenomenon astronomers call the Great Attractor, a gravitational anomaly about 150 million light-years away that pulls the Milky Way and thousands of neighboring galaxies toward it at roughly 600 kilometers per second, a dense band of stars and dust in our own galaxy's disk. Blocks direct visual observation of the Great Attractor, a region astronomers call the zone of avoidance. So most of what we know about it comes from radio and X-ray surveys that can see through galactic dust. Beyond the Great Attractor sits an even larger structure, the Shapley Supercluster, containing more than 8,000 galaxies, and pulling on an even greater scale. But the same acceleration that reveals structures like this is also erasing our future view of them. Galaxies visible to us tonight will eventually cross a horizon their light can no longer outrun, one by one dropping out of visibility, as the space between us and them stretches faster than light can cross it. Calculations suggest that in about 100 billion years, astronomers on Earth, if humanity or anything descended from it still exists, will look up and see only the stars of the local group. Every other galaxy the entire cosmic web we can map today will have receded past the horizon, leaving future observers with no evidence any of it ever existed. If eternal inflation describes reality accurately, our observable universe amounts to one bubble among countless others, each one forming when inflation stopped, in some pocket of an eternally inflating background. Physicist Max Tegmark has cataloged several distinct versions of this idea under the label Multiverse, ranging from simple variations of our own universe, far beyond the horizon, to regions where the physical constants themselves came out different during their own inflationary event. None of this counts as confirmed science. No experiment has found or ruled out another universe, and by most versions of the theory, no experiment ever could, since anything beyond our horizon is causally sealed off by definition. Cosmologists take the idea seriously mainly because it falls out of equations, inflation, that already explain other things we have directly measured, not because anyone has seen evidence of a second universe. Turn a radio telescope toward any patch of empty sky, and you pick up a faint, uniform hiss of microwave radiation, leftover light from about 380,000 years after the Big Bang, the moment the universe cooled enough for atoms to form and light to travel freely for the first time. Arno Penzias and Robert Wilson detected it by accident. In 1965, while testing a radio antenna in New Jersey, mistaking it at first for pigeon droppings, interfering with their equipment. That signal, the cosmic microwave background, gives astronomers their oldest direct image of the universe, from a time when everything that exists today still existed as an almost perfectly uniform mixture of hydrogen and helium. Every atom heavier than hydrogen and helium in your body came from inside a star, carbon fused in the core of a star, roughly the mass of our sun, near the end of its life. Calcium and iron formed under conditions only a supernova can produce, when a massive star runs out of fuel and collapses in under a second, then blows itself apart, scattering its contents across hundreds of light years. Astrophysicist Carl Sagan popularized the phrase star stuff in the 1970s to describe this, and the chemistry backs him up literally. The calcium in your bones, the iron in your blood, the oxygen you just breathed in, all of it was forged inside stars that finished burning long before our sun existed. That material drifted through space for hundreds of millions of years before gravity gathered a portion of it into the disk that became our solar system, then into Earth, then eventually into you. Cosmologists call the current period the Stelliferous era, the stretch of cosmic time, when stars can form and burn. It began a few 100 million years after the Big Bang, and by most models continues for roughly another 100 trillion years, before the last red dwarf stars run out of hydrogen. After that, the universe enters a much longer stretch, dominated by white dwarfs, neutron stars, and black holes slowly evaporating. Through a process physicist Stephen Hawking described in 1974, a process so slow that a black hole the mass of the sun would take about 10 to the 67 years to fully evaporate. We exist inside a narrow window of that timeline, early enough that the sky is still full of galaxies, late enough that stars had time to live, die, and scatter the elements that built a planet, and then a species able to measure any of this. Remember that number from the start, the one describing the size of the universe? None of this makes it any smaller. That's 93 billion light-years of observable space, somewhere between 200 billion and 2 trillion galaxies, depending on which count you trust. A horizon expanding away from us in every direction, faster than light could ever cross it. Every fact in that number passed through a chain of stars, supernova, and 13.8 billion years of drifting matter to end up arranged into someone who could measure it. Look up again tonight. You're the part of it that happened to end up asking how big it all is.